For this, you'll need a copy of the heat of formation chart that I posted in Classroom. If you want to print it out, we'll be using it a lot the rest of this unit, but if you just want to reference it online, that's okay too. So how we calculate that heat of reaction. The formula for it, I guess you could say, is the heat of reaction is found by taking the products. So I put in brackets because I think that's how it's normally shown, and I think it's a good organizational tool. So we take the value of all of the products added together, and we subtract from them the value of all of the reactants added together. So remember, in a chemical reaction, you'll see here, we're going to complete and balance sum in order to do these problems. The products are the things on the right-hand side. The reactants are the things on the left-hand side. So all of the products minus all of the reactants. First example for you is find heat of reaction for the combustion of C4H10. Combustion, burning. If you need to review some reaction types, you can. But for combustion, we are taking whatever is being burned. We are adding oxygen, which is a diatomic. We are making carbon dioxide and water. The easiest order to balance in is C, then H, then O. So 4 C's on the left means I need a 4 there. 10 H's on the left means I need a 5 there. Here you'll see we have 8 plus another 5 oxygens. That's 13. That's an odd number. So I put the odd number over 2 as my coefficient. Okay, so that's my reaction. Now I can do heat of reaction by doing products minus reactants. But what on earth do I mean products minus reactants? This is where that chart comes in. We're going to have to steal values off the chart. So if you haven't opened it yet, this is what that chart looks like. There's the first page of the chart and the second page of the chart. I want you to know right now that this thing at the bottom of the second page that says average bond enthalpy has nothing to do with what we're doing today. It's just on there for when we're printing and saving paper in person. Okay, so I need to first get the value for my products. So my products are CO2 and H2O. If we go to that chart and we look at CO2, you'll notice actually that the chart is pretty much in alphabetical order. So CO2 would be second column right here. And it has a value of negative 393.5. Water on your chart actually has 2 values. So there's water as with the little G next to it means gas, and water as a liquid. If I ever wanted to tell you if it were gas or a liquid, I just put that G or that L. But what we actually require that you know is that for combustion reactions, we are always going to use water as a gas. And so we're going to be using a value of negative 241.8 for water in a combustion, in a burning reaction. I tell people to think about something burning, think about a candle burning. You can picture steam leaving from the candle. Steam is water as a gas, but you can't picture water dripping as a liquid out of that candle. In real life, sometimes it's a gas, sometimes it's a liquid that's produced. We're always going to use it as a gas. Just think of the fact that you can picture steam from a combustion reaction. So let's go up and label those values. For the carbon dioxide, that was 393.5. We have 4 of them. Sorry, wrong one. So we're going to actually need to take 4 because of the coefficient times the value from the chart. And for water, we're going to have to take 5 times the value, again, of gaseous water on the chart, negative 241.8. When I go to look at the chart for C4H10, it's a little weird looking. I purposely chose all the weird examples so that you won't get tripped up with them in the future. C4H10 is right here. It has a little N in front of it. So does the one below it. That N means something that you haven't learned yet. Don't let it throw you off. It's still, if you ignore that M, comes in alphabetical order on this chart. So that has a value of negative 124.7. I don't have more than one of them, so I don't need to multiply it by anything. And then for oxygen, oxygen is a diatomic, but it's a pure element. For any pure elements, meaning an element by itself on the periodic table, so it could be iron, it could be lithium, it could be oxygen, which is a diatomic, any element by itself is not listed on your chart. Pure elements have a value of 0. So if you look at the second page of your chart, you'll see some ions. Ions are not the same thing as pure elements. Ions do have values. They're on the second page. And let me give myself a little more room here. So that has a value of 0. I could technically, I'd multiply the 0 by 13 halves, but we know it's still going to be 0, so I'm not going to bother. That was just me organizing all my information. Now I'm going to do products minus reactants, right-hand side minus left-hand side. My heat of reaction equals, I like using the brackets to organize it all. 4 times negative 393.5 plus, because these are still products, so I'm adding them all together, 5 times negative 241.8. Close the brackets because we're done with the products. Then I will subtract out in brackets all of my reactants, negative 124.7. I could say plus 0, but those are all of my reactant values. This isn't that hard. Where people go wrong is typing it too quickly in their calculator or doing funky things with the negatives and switching this negative to a positive, whatever. My recommendation to you, simplify what goes in each bracket in one step and then type it in your calculator in another step. So when I do 4 times negative 393.5 plus 5 times negative 241.8, I get negative 2783. And then the right-hand side simplifies to negative 124.7. Then in my calculator, negative 2783 minus negative 124.7, I get negative 2,658.3. And if you look at the top of that chart, it reminds you what the units are. It says at the top of each column, kJ per mole. And that should make sense because when we used all of these heat of reaction values, they were always given in kilojoules per mole. And that led us to the proportion where we could find a different number of kilojoules for a different number of moles of something in the reaction. Let me show you one more example. Heat of reaction when magnesium nitrate dissolves in water. So as a quick refresher, something dissolving in water, we don't actually write the water. We're just taking what's dissolving and splitting it into its ions. I balanced it as I was going out of habit, but that's why this 2 is here, is to balance that too. Okay, so the ion values are going to be on the chart. They are not pure elements when they're ions. They're going to be on page 2. So magnesium, if we look here, magnesium has a value. And honestly, if you forget what's charged something has, this chart is kind of like a nice little cheat sheet. Magnesium has a value of negative 462. Nitrate, we need to multiply it by 2, but it has a value of negative 206.6. And then, let me go back to the first page, sorry. When we're looking for magnesium nitrate on the actual chart itself, if you look alphabetically and you're trying to find it and you can't, it should be somewhere around here-ish, and you don't see it. That's what this little dot is there to remind you of. That means we wrote it in at the bottom somewhere for you. So magnesium nitrate has a value of negative 770.9. Negative 770.9. Then I can find my heat of reaction by doing products minus reactants. Again, you have to show this work on your paper. If you don't want to simplify it on your paper, again, I think you're more likely to make mistakes, but that's okay. But this first line here, you do have to write out. I do like to simplify So negative 462 plus 2 times negative 206.6 gets me negative 875.2. And then I'm subtracting out the negative 770.9. And this, sorry, I'm out of space, I get an answer of negative 104.3. Kilojoules per mole. Go try. If you get something wrong, make sure you're writing it in the correct order. Make sure you're multiplying by the coefficients. But that's that.